we aim at defining a bit better what is frequency dependent and frequency and time dependent grid impedance. And there is no real consensus about that. There is no definition. We just use our own methods in different institutions, in different publications. So we try to set a bit some light on that. Another objective is to develop techniques that could be used in standardization. For instance, laboratory trials of power line communication channel. There are not so many standards about how to test power line communication devices, and to see that the impact of the grid impedance is also taken into consideration. Finally, maybe also to have a reference impedance to compare measurements with filters, or to see how active or passive filter interact with power line communication. So it would be good to have some reference in frequency domain and time domain. HES-So ValaisWallis is located in Sion, Switzerland, and the group that work on this project is the Industrial Electronics and Drives group, where we have converter design, EMC, filters, control of converters, testing of converters, and also hardware in the loop competence and infrastructure. The project partners, I summarized here, it's a bit too detailed for presentation now, but we have one institute of metrology, METAS, in Switzerland. We have 3 industrial partners, Schaffner, EMC, mainly filter designs, SEG with utility, Camille Bauer Metrawatt, who is designing power quality instrumentation. So a large spectrum of industry too. We also have a participation by European universities, TU Dresden and UPW in Bilbao, and an industrial company who defines and work on power quality and design impedance analyzer, more energy. The whole thing was founded by the Swiss Office of Energy, which is maybe important to mention here. The expertise of the different partners, you can see if you consider power line communication system over the grid section, we have a bit competence in all the domain of that, from filters to measurements to analysis of grid impedance. The project helped us to better understand and to better model line impedance in frequency domain mainly. The device, static programmable time varying line impedances, have been developed and tested with some success. We have then had the chance to compare different impedance analyzer. I think this is the first time that it was ever done. And it helped us to gain expertise to report this towards standardization or utilities. So we start with the static line impedance reference. And the goal of it is to maybe have a tool to compare grid impedance meters, for instance. So the comparison was very much dedicated to that. First, the definition. What do we need as a static impedance reference? There are already references defined by standardization communities like CISP 16. Now, do they match the need for power line communication in the frequency range 3 kilohertz to 150 kilohertz or even 500 kilohertz? There have been many measuring campaigns, for instance, DARCZ campaign, ended in 2018, involving TU Dresden, for instance. And the results is that most of the measurement on the grid show a lower impedance in the domain of power line communication. So what does it mean? It means mainly more attenuation possible. Another aspect of it is there are resonances that can appear. And if we design a spectral impedance analyzer, we need to show some resonance effect and to see if the device is able to detect these resonances and to assess the impedance correctly. So we have added to the standard CISP device, the V-AMN from CISP 16, we have added a network that show a bit more resonances and drop generally the impedance in the frequency domain of power line communication. So we can then test the parallel connection of those two devices. This is the detailed design. If you are interested, we don't need to go in detail, but it's made with passive component, actually RLC resonance circuits. The device has been developed by Metas and then characterized by Metas mainly in unenergized status. But then we have shared this device. The same device has gone through all the institutions that took part to the project, and they've made their own tests. 4 grid impedance analyzer were available that can measure energized impedance on the line, 230 volts, and then Metas has used a network analyzer that is not able to measure energized system. Here are the different comparison of the different characteristics of those devices. Maybe what's important, the devices use an excitation source in most of the cases. Some are active, some are passive. The sweep of frequency can be done at once with a sweep, or then by single frequency steps, or finally with randomly pulsed signals. So very different techniques are involved in this comparison. The signal processing also show very clear differences. Mostly, of course, Fourier analysis. There is a time sample, a window, and there is a Fourier analysis on that window. HES-So Valais use a bit different. We use the lock-in amplifier technique, and it means a very high resolution in noisy environment. Here are the results of this comparison, and you can see that 2 rounds. On the left is the first trial, and the second trial that was done by some institution. And we can see that there is a very good correspondence despite the differences in techniques and analysis that is used. We can also see that it was also giving the chance to fine-tune equipments within the process. So we are very satisfied of these results, at least in the PLC frequency range. There is very, very good correlation between device in the energized tests. I'm a bit busy, so I jump already to the programmable and time variant reference impedance. And this is more to show how to give flexibility to the device, to get more resonances at different frequencies, to give different magnitude and phase behavior of the impedance, as well as to emulate the behavior of converters with the switching modes and different impedance in time. It was realized by Metas, and it is a device that comes very similar to the previous one. We have the impedance meter, we have the line impedance network, standard line impedance network, and then we have here these different resonance circuits that can be commutated by a computer, a control array. So detailed schematics for the ones who have interest. And you can see here all these different resonance circuits that can be controlled and put in parallel to the circuit or not. This gives a huge amount of different curves, and they were all calibrated step by step by Metas. It's their core competence to calibrate those devices. And they also designed a very handy control interface so that you can control and select all the different capacitance and inductance and resistance in the circuit on one side. And then with the help of a synchron signal, you can synchronize with the AC voltage, and you can then switch different impedance during one subcycle of, or one cycle of the grid 50 Hertz period. Again, the device was tested by different entities and different impedance analyzer with more or less success. And this is, again, the same devices that they were presented. Here we show simply that 3 of those devices can work in subcycle and make a very fast impedance measurement and record it. With the lock-in amplifier technique, it's very difficult to do that, and it takes time. You have to filter out the signals, and this is mean that our technology is not very, very good to use below 10 kilohertz. So we don't sell that feature. We have used the same way, the system, to make this test. The network is replaced simply by the time variable impedance, and we had to select all these scenarios. To make dynamic testing especially is very challenging, because we have resonance circuit in the device. When you change the device configuration, you might have large oscillations. So we cannot compare so well different devices when the impedance that is measured does not show a stable behavior in the condition we are testing. We had also to make selection for different criteria. So we finally kept 3 scenarios that we compared with the different devices. And the results were not too good, and there are different reasons. We think that the damping can change a lot on the behavior of the measurement if there is a damping in a circuit. We have a bit the feeling that there is a bit too much capacitance in the device, because we can see here, for instance, that when it's not connected to the grid, we have some behavior, mainly inductive, but when we measure the energized device, we get similar results, but we get a lower impedance in the high frequency range, more oscillations, and so on. So there are parasitic components we think that are not clearly behaving the same when they are energized or not. So this is the first attempt. In the low frequency range, when we don't make switching between different topologies, it works pretty fine. In the higher frequency range, we can also see that one of the devices was showing a bit funny behavior. For instance, we have very good tendency, but there are superposed variations, And that could be because of different switching to the neutral, to the earth. All that has to be clearly settled and defined, that we can make a second round of comparison in more steady conditions. I don't show all the results. There are so many. It would take more time than I have available. The dynamic scenarios, the subcycle measurement, were compared with the measurement from, for instance, from UPV EHU, which was working very well, apparently. It was compared with simulations that we have done in MATLAB, LT-SPICE, sorry, and all these different impedances according to the cycles are represented here in time. So you can see on the time axis on the left here from 0 to 20 milliseconds and from 1 kilohertz to 500 kilohertz. And you can see that the tendency is pretty good with resonance in the same levels, but there are some phenomena also that appear, maybe not in the similar way or expected way in the middle. So again, the tuning and the fine tuning of this has to be worked out, and especially the working condition for those tests. So to the conclusion for this main part, we have shown that the static independence has shown very promising results, and we can align with the CISP16 standard, but with a different behavior that is very well dedicated for power line communication applications. Stability at switching times has really brought it to trouble the tests of the programmable impedance. I think at this stage, we have a good programmable impedance, but not good enough dynamic, especially in low frequency range. In high frequency range, the devices and the parasitic component must be also checked. For the next part of this, we have a project to have uncertainty of static impedance evaluated in the frame of Ampere Grid ME project. We have need to maybe move towards comparison with converters, select a couple of interesting converters and check all these impedance meters. We can also include further impedance meters to the ones who are interested. And then maybe we also will involve hardware-in-the-loop simulation tools for the evaluations. I'm running a bit over time. So the standardization activities are very much summarized in collaboration with the working group 11 of CENELEC TC 2019, mains communication systems. There is immunity standard for power line communication device dedicated to smart grid or smart grid infrastructures. And then there is electromagnetic interference report. We are working on the first draft where we will give the result of the project and some recommendations. What is interesting, maybe in the standard, in the last development, and this is the end draft, final draft for votes, there is inclusion of parallel components with specific impedance in the test of the influence on the communication quality. In the working group 8 of Technical Committee 77, we have an extensive technical report on grids in the influence of power converters, where we describe resonance phenomena linked with power electronic equipment, impact of modern power electronics and filters in the propagation and amplification of distortions or signals, and different aspects with modern grids are studied, and of course, frequency-dependent grid impedance plays a very important role in this report. As a last note, maybe behind the labs, we had the chance with colleagues from Kami Bauer, who are partners of the project. I think Thomas is here. And we could measure on site the impedance in a very nice site in the Swiss Alps with 3 impedance meters. And it was a basic transformer station, no complicated location. And this is the first on-site comparison of 3 impedance meters. As a prime, I show you the preliminary results, and you can see that they are very positive. It's a network with not too many resonance, and it's a bit difficult to decode. There are maybe too many curves, but case by case, it's always matching very well between 1 kilohertz and 150 kilohertz. So it looks pretty good for this 3 device on field in normal situations at least. And this is a static impedance. Thank you for your attention. If there is still time for questions, I'm pleased to answer.
Yeah, Dominique, thank you very